Hello, can you guys hear me?
Yes.
Okay, thank you for responding. Nice. So, so today is week 15, lecture B. Okay, lecture B. We still have some slides left over for the brush, brushed DC motors. Okay, so these are the contents for today first, part one. Then later part, we are going to cover brushless DC motors. So we are going to talk about controls of DC motors and its gear systems and gear ratios and motor selection rule of thumbs and those considerations. Okay. Okay. So here we come to the control part. Okay. So talking about control, you need to ask, what is the task? Okay, for the motor for what? Okay, because you have a wide range of the speed and torque relationship. Um, so a conventional servo uses a DC motor simply as an actuator for motion control with the position and speed control. But sometimes you also need a torque control. You don't want to apply too much torque to damage things. Okay, so those torque must be controlled. So these are the three things you can see: position under control, speed under control, or torque under control. Okay. So for the control or methodology, basically you have a field side and amateur side. So it's a field and amateur. Remember this equivalent circuit. So you have something like this. Okay, so then you have a load shaft connected to a load. So we are going to go through this armature control and field control respectively. And so we are going to talk about armature control, as it says, is to control the field current in the stator circuit. So the VA is my armature control. Only change the VA, while the field is constant, not changing. Okay, but you may say, oh, they can be collaboratively controlled. That's too hard. Make the structure expensive and complicated. So we keep it constant. So this also includes permanent magnet, okay, kind of DC motors. If you want to keep the torque constant, you have to keep the armature current constant. Okay, and because here the field current is constant, therefore the voltage VA directly determines the motor back EMF. Do you still remember EMF? The electromotive force after a Lorentz is made for the impedance drop due to the resistance and the inductance of the armature circuits. Okay. Then another one is to change the field. So then we keep the armature voltage as a constant. We change the VF. Okay. That is the field excitation circuit to generate the magnetic field. Okay. So if the IA may not be able to keep constant, then the torque provided by the motor will change. So that's a change is proportional to the IF. Okay, IF change. So remember, we are using something like virtually, meaning it's not exactly constant. So we are going to see some of the characteristics. Okay. Another type is DC servo system using a position feedback and velocity feedback. Okay. And in the motion control, we also have to do the torque control. Okay. So if the torque itself is the main concern, okay, like you are doing a metal forming operation and tactile operation and so on and so forth, those small motion error will produce very large unwanted forces, okay, like in those parts assemblies, assemblies. So then the motor torque must be under control, okay. So of course, using a torque measurement is necessary, okay, like using a strain gauge sensor. Okay. So here is a schematic diagram of a DC servo system. Okay. So you need the servo for what? Okay. Servo for position, velocity, or torque. Okay. Or torque. So this is the load. This is the coupling shaft. Okay. The shaft will transmit the torque to the load and bring it to turn. Okay. So in here we use RVDT to measure the position. Do you have an idea what's this? Potentiometer. Okay, potentiometer. In many cases, you may not use there's a full circle, right? So you only have this small trouble of the angle. So then you can have a speed measurement. Okay. Then this is the motor. Is also called plant to be controlled. Okay, controlled. So you could measure the armature current. You could measure the torque. So these are the feedback signals. Okay, these are also feedback signals. So this is your reference input. So inside here, you have to do two things. First, you do decision based on those feedback and reference. Then you do control. Okay, control, including the controller structure. You can use PID or some other controls. Okay, so that's the block diagram. So if you check the armature control, meaning you have a VA, this is the input VA. So then this is back EMF. Okay, so minus this one, you get V. This V will go to armature circuit, and then you generate a magnetic torque, and minus the torque from the load, then you feed, but this is a Newton's second law, right? So Newton's second law, like Jm theta double dot. So this is the omega. The omega dot, okay, is the torque, okay, total torque. Of course, you have a viscous friction term, so that's proportional to omega, okay? So you should minus Bm and omega, okay? So that's armature control DC motor block diagram, okay? Block diagram. But this is not a controlled system. So basically this is called a plant to be controlled. Be controlled. And we usually say this is a G of S, okay? G of S. Or the G of S is basically from those physics-based modeling. We'll get these parameters and get this G of S. But what you really need to do, like here, we do a output omega is things to be controlled. Then I should give a omega desired, okay? Omega desired as my set point. Then I have feedback in here and measure this guy and pull out here for feedback, okay? So inside here, you need to put a CFS. That's the control system big picture. So everything we see in original slide here is nothing but what? An open loop. So it's open loop. I hope you have thorough understanding about this open loop model GFS. There are many, many ways to design CFS. So we're not going to cover here. Just you see the big picture. So that's for armature control. For field control, it's a little bit different. So you have field VFF going through the field excitation circuit, IFF. Then you have electromechanic conversion. In case of A, you get the magnetic torque, and you have minus. So this is more clear cut. Remember here, again, we should close loop through something we had. It's called omega desired, so minus. So this you put here CFS, your control, okay? Sometimes this is, in this specific case, is called velocity servo controller, okay? That is this. So here, you don't have to bother the back EMF, okay? Another idea is to have a outer loop control using what they call PLL, phase locked loop control. Phase locked loop, okay? This is L is loop, phase locked loop. We'll see the picture here. So basically, you have a command generator giving a pulse train. Then you have a shaft encoder, have a feedback to have a phase detection. I want this phase to be the same as this. If there is a phase difference, I'll generate some signal. Low pass filter, only keep those low frequency and those high frequency carrier signal. We are not going to care about it. Then you drive the motor amplification, then you drive the motor, you get motor rotation. So that's a position servo. Okay, position servo. Okay. So that's the basic control side. And next is regarding a mechanical coupling. Usually you have gearbox. Okay, so you have a motor. Usually this is very fast. Okay, this is fast. But what if my load, we don't need that fast. So you need a gear ratio to reduce the speed. So in this case, let's assume we neglect the gear backlash and elasticity. So we assume everything is rigid. Okay. So in that case, so this is called gearbox connected gearbox. But you can remove the gearbox, then these two shafts will connect together. Then this is called a DD, because direct drive, okay, direct drive, okay. So these two situations are usually used in practice. Many of the robotic systems, they have direct drive today because of the technology is changing. So that direct drive is much easier mechanically, and also the cost and the mechanical parts are less, okay? So in that case, N is 1, is direct drive, okay, direct drive. So when we have a gear, then we have to talk about gear ratio. There is an interesting argument regarding gear ratio because gear ratio will amplify the J1. J1 is this side, the motor side, okay? lumped into the original one. This is J2, load inertia. J has an official name that is called moment of inertia, okay, MOI. So then you can see there's M square in here. So this part you cannot ignore, okay? That's why the motor moment of inertia will be counted in the load side. This is the load side by have N square, okay, N square. On the other hand, the motor inertia, this is J1, the motor inertia, J1, often the dominant inertia in the servo system, okay? So you can see some examples. You amplify N square, okay, N square. Okay. So when you buy a motor, you really need to check its inertia, MOI, okay? Because if this is too high, it will add onto here to make your system overall sluggish, okay? Therefore, the choice of N, capital N, is very important. It's very important. And let's do an argument here. However, so we have seen omega 2 is my angular speed of the load, okay, of the load. On the load side, okay, load side, I'm going to have something like this. I want to check what can make my acceleration. This is my load side acceleration, the highest, okay? So then we do a DDN to check the N, change the N. So it turns out that we have this stationarity condition. Then there is an optimal choice of capital N. So what is the optimal choice? Optimal in what sense? Is to make the acceleration maximum possible. Okay. So it will be J2 over J1 square root. That is beautiful, right? So you have to choose the N close to this value. In the spec, you should usually get J1 and J2, okay? So that's it. Another thing, consider the speed torque curve, okay? So this is speed, this is torque, okay? So when speed is 0, the torque is called a stall torque. When speed is maximum, then the torque generated will be very small, 0. Okay, so therefore there's a linear relationship from here. This is a linear relationship. So we can usually say, oh, the higher the speed, the smaller the torque the motor can provide. Okay. So what is the speed power curve? So if we check the power is the speed times the torque, okay, times the torque. So it becomes speed torque becomes a parabola. So the power is 0. It's 0. So meaning you are not moving, then you don't suck any power in here. Okay. But if you move very fast, okay, and you don't have a load, a torque to carry, then your power is also very small, very small. So in between, there is a peak point in here. So if you want to have your motor working in maximum power, then you should not go to a new load speed or the stall 0. So there's something in the middle. So usually we depend what is my load power point A and the point B. So depending on the same speed, okay, same speed. So the power maximum is here. So you can produce different load power. Okay, load power. So this is the real load speed. Okay, so the power that can provide is here. Okay. So it's difficult to always maintain the power at the maximum point. So this is called MPP, maximum power point. Okay. But this is only says that we have the peak power that can provide. Okay, provide. The maximum speed will not be the same as the peak of the speed. So therefore, you understand there is a trade-off. There's a trade-off. You should always check where is your OP, called operational point. You're at what speed and what torque and what power. Okay. So in selection of the DC brushed motor, we're talking about DC brushed motor. So these two primary considerations of what torque you need and how fast you move. Okay. So manufacturer will give you a data sheet or specification sheet available to include these. What are the mechanical time constant, speed at the rated load? Rated meaning you are allowed to usually run on this load. Not too big, not too small. Then you have a so-called rated torque. You have a frictional torque, that's a PM term, omega, okay, PM omega. And what's the dimension, of course, what's the weight. They also give you a no load speed, meaning you have a shaft not connected to the load. Okay, so this is your motor. Okay, so then you don't have the load, then you see what is the omega. Okay, omega no load. Omega no load. Then when you have no load, how fast you can turn. So this is acceleration. That's d omega dt. Remember. And rated output power, damping constant, armature moment of inertia. Okay, so that's for the rotor. Excuse me, rotor. So that's the J1. So those are on the mechanic side of a specification. You also have electrical side, like electrical time constant. So say for example, you have armature resistance and armature inductance. Okay, so these should be known. And so that voltage current, those compatible drive current. Okay, specifications. So you should not go outside the range. Input power, field resistance is RF, LF. Okay. So then other things like brushed life, how often you should change brush and how often you change motor. If any of you want to zoom in, I suggest you choose brushless DC motors and check one of the spec sheets to answer all these questions. Not only that, there are other factors you should consider, like heat transfer and coupling method, efficiency, mounting operation, and temperature, and environmental humidity and temperature. Okay. So yeah, as a designer, you should care about these things. That determines your load, torque, power, cost. Okay. And also what's your load. Okay, what's your load. So I'm going to go a little bit faster. Let me see. Power. We have seen this picture before. Cost. Okay, so I think choosing a motor, you need some real world examples to work with and build it and see it. And there is a very interesting website. It's called Motor Cuck. Motor Cuck. So, do you see this for Motor Cuck? Motor Cuck. Okay. So, mainly focus on model aircraft power system selection using a computer called Motor Cuck. Motor calculation. Okay. How to choose that the motors. But I have to tell you that in aircraft, they never use brushed, okay, DC motors. They usually use brushless, okay, brushless. So that answers next module we are going to cover is what is brushed DC motors. I have 88 slides, so we are going to go through many of these, okay? So to understand, we are going to do this mainly, brushless DC motors. Okay? To understand that, you better to understand some common knowledge regarding what they call rotating magnetic field electromechanical system devices. So this is mainly linked to the air gap. It's called magnetic motive force. MMF. Those magnetic field is rotating, okay, rotating air gap, okay. This is pretty tedious and not very interesting. The only message I hope you can remember is that what they call brushless is also called BLDC, okay, BLDC, brushless DC motor, okay. In the final exam, we'll have a section about 10 such kind of abbreviations, okay? And if I ask you to tell me what is BLDC, it's so widely used, and you don't know that, that's your fault. You didn't attend my class. Let me see how many people. We have 15 only, 14 actually, minus myself. I have less than 1/3 of students showed up, okay? But I assume the rest of you will go through the recorded lecture, okay? So if you complain in the final exam saying that, hey, why there's so many things I didn't know, because you didn't learn, okay? So we're going to talk about electromechanic motion devices. There are something called reluctance devices, induction machines, and synchronous machines. And this one actually is easier, okay? It's easier. So this is called permanent magnet devices, okay? So let me remind you, last time I talked about linear motors, okay? Sometimes they do a PM RAM using a permanent magnet linear motors. So the motor will move not rotational, but linearly, okay? And to understand that, you really need to understand the magnetic motive force, okay? Magnetic motive force and the air gap, through the air gap motion, okay? Okay, let's move. This part is important in the sense that in the real world, brushless DC motors are used more and more. In a lot of UAV drone propulsion system, they are using brushless DC motors, okay? Again, DC motors is actually AC motors, okay? Alternating current. So let's do that, okay? We're talking about, remember in the DC motor, okay, brushed DC motor, the magnetic field is static, okay, not changing. So therefore, there's something called stator, okay, stator. But here we also have what they call stator. But however, the windings will have different arrangement such that the magnetic field that's generated is not static. It is rotating, it's rotating, okay? So again, we have we have seen that the DC motor, you have windings on both stationary and rotating members. Okay, so these circuits in relative motion, and therefore you cut the flux. It's called flux cut, magnetic flux cutting. So therefore, because of the cutting, you convert mechanic to electrical energy, or convert electrical energy to mechanical energy. So that conversion is realized. So that's talking about DC here. Due to the action of commutator, the resultant magnetic motive force produced by the current flowing the rotor windings is actually stationary. So that magnetic field is not changing, okay, remember. So the rotor windings appear to be stationary magnetically speaking. So the current in the field winding, a torque is produced by the rotation result due to the force established align these two stationary orthogonal magnetic fields. So that's the DC part, okay? So if we are not talking about DC, okay, so then the torque could be produced as a result of one or more magnetic fields rotating about the air gap of the device. So so then we have different types. One is called reluctance machine, one is called induction machine, one is called synchronous machine, a stepper motor, and brushless DC motors we are talking about here. So it is brushless DC motors, also called permanent magnet synchronous machine. So it's a synchronous machine. So they develop torques in such a manner that the magnetic field is no longer static. Okay. So what's in common of all these what I called AC machines, AC motors? Okay. Because the common thing is the winding arrangement of the stator. You still have a stator, and so that's how they have that winding. And another thing is the generation of rotating magnetic field. We'll keep saying this term, okay? So you add the stator current in an alternative way, then your magnetic field is changing, okay? Okay, so these called common features of a rotating magnetic field. So let's go through some pictures in here, okay? So this is called two-pole single-phase stator winding. Okay, again, this one is go inside for the conductor, the coil. Okay, this one is coming out of the paper. Okay, so it's called the winding going outside. Okay, the current going outside. So in here we put. So you can see there's an air gap in here. So there's air. These are the air gaps. Okay, this air gap. Exaggerated. So you have windings on the stator. Okay, windings on the stator, and you have different coils. AS3, AS3 prime. You know these coils. Okay. Okay. Usually you can see this is a coil is like a rectangular. Okay. Rectangular. Okay. So in the AS side, so you have you don't so you only have a rotor and stator like this, and you have something the rotor can rotate because of what? Because of the rotating magnetic field. So the magnetic field is moving like this. It will drag, okay. Okay, it will drag or pull, or not pull, it's just like drag the rotor to rotate because of the rotating magnetic field. So go a little bit quicker. So if you have two-phase stator windings, okay? Like A is like phase A, B is like phase B. So that kind of arrangement, they put what they call the quadrature arrangement, okay? So you put the AS and the BS in here to excite it, okay? Then you will have a rotating magnetic field so that you can bring, this is my rotor, armature, okay, rotor, we will call rotor, okay, to rotate, okay, to rotate. Of course, the coils can be arranged. So this is just a two-phase stator winding. You can have multi-phase. Okay? So to generate an air gap magnetic field, okay, magnetic motive field, the stator winding approximated as sinusoidally distributed windings. Okay, let me show you the picture. So some places you have more, okay, some places you have less, okay. So this is a two-phase, okay. So therefore, you are generating a sinusoidally changing magnetic field. Okay, magnetic field. Make sense? Okay. So the developed diagram with this what they call sinusoid distributed stator windings. So those are conductors for the different turns. Okay, different turns. So if you cut this rotor's angle is 5 of S. So you can see from 0 to 2 pi, you have a stator in A, stator in BS, AS, okay? So you have two phases here. We can derive such that you can see I have a rotating magnetic motive force is proportional to your angle. So it's sinusoidally changing, okay? Sinusoidally changing. So remember 5 of S, what they define 5 of S is this one. This is the angle. Okay. Angle is the motor's relative motion. Okay. All right. So if we want to see the closed path, is to establish this rotating magnetic field. Okay. So this is the way you can see. Okay. So again, the coils are arranged in a sinusoid approximate setting. Okay, the setting. So we have seen this already. So that's for one pole. Now let's talk about more cases. So we have two poles, single phase, sinusoidally distributed stator winding. So we have something similar. We're going to go to, so these are the two phases, two poles. Let's check. This is commonly used, okay? So it's called three-phase, okay? Three-phase. Therefore, the coil connection is like this. So you have three-phase AC current, okay? AC voltage. Okay. Then you will produce sinusoidally rotating magnetic field. Okay, okay. So yeah, there are the phase relationship. If this one stay in the middle, then the other phase will be minus 60 degree and minus 120 degrees and plus 120 degrees. So that's the three phase. Okay, three phase. Of course, three phase and two phases, the generated MMF formula is different. Okay, so that's give you a rough idea about phases and poles and how you generate rotating magnetic fields. So we talked about rotating electromagnetic devices, synchronous, induction, and direct current. So we don't talk about direct current right now. Those are DC motors. So synchronous machines. Why we call an AC machine a synchronous machine, AC motor as a synchronous machine? Why? Because they develop an average torque only when the rotor is rotating in synchronous, okay, with the rotating magnetic field, okay. So if you have a current flowing in a stator winding, you generate, okay, rotating magnetic field, and the rotor will move synchronously, okay, with that magnetic field. So the synchronous machines are like reluctance machines, stepper motors, PM machines, BLDC. So they are just synchronous machines. You may ask, what is the asynchronous machine? Okay, let's see. We don't call asynchronous machine, we call induction machine. Okay. So it's a principal way to convert energy from electrical to mechanical, those motors, okay? Those induction machines, you cannot develop a torque. If you synchronous, okay? If you synchronous to the rotating magnetic field, then you cannot generate torque. It's useless. The windings on the rotor, they are actually short circuit. So current flow in this winding, you have a torque interacting with the air gap magnetic field for the stator winding. It's rotating, okay? So in other words, to have torque generated, the motor must be rotating at a speed not the same as those synchronous speed. When we say synchronous speed, the synchronous means the rotating magnetic field rotating speed. So you have some small difference. That difference is the cause of producing the torque, so that the motor is useful. Okay, so that's called induction machines. So yeah, those winding arrangements, probably we should skip these. When you buy a motor, you don't want to disassemble and see how the windings are arranged. Many years back, when I was an undergraduate student, we visited the iron and steel company works there, and we checked all those different types of motors. Some of them are huge. You can climb inside of the motor. So I have a first-hand experience about winding arrangements. But I see today, you just buy a motor, you use it. If it's wrong, we just buy another one. You don't want to fix the windings yourself. So, let's see. Reluctance device. That's asynchronous. It's a synchronous machines. Let's go through a little bit slowly. Like a single phase, two-phase, two-pole reluctance. So we'll see a picture in here, and how this can be actually moved. So it is a little bit hard to understand if you do not understand this rotating magnetic field. So I assume that you acknowledge that there's a rotating magnetic field going on, okay? You don't see it, okay? See it. And that rotating magnetic field will start to drag the rotor to rotate. Let me see. Let me see. So how you generate those rotating magnetic fields, because the windings are sinusoidally distributed, so that it will generate that way. So the operating principle I think this LE. The principle of operation is like this. You generate a force in an attempt to minimize the reluctance of the magnetic system. Say, for example, I give you a thought experiment. So you have one magnet, you have another magnet here. So they are not aligned. So there is an intrinsic tendency they want to get aligned. N and sector to S, North Pole and South Pole, they will stick together. So there's a traction, okay, between that. So in other words, you have a force there, try to minimize the reluctance. Think about reluctance as a resistance, okay? In a magnetic circuit, you call it reluctance. So you have to stick them together. So that's the basic principle. North will be attracted by south. South will be attracted north, okay? So that kind of attraction, once you get aligned, then you have a minimum reluctance between N and S. So if you have slightly shift, you'll get it back again. So we already said that we have AC here. We have AC flowing in the winding of the single phase stator, okay, it's alternate current. And so therefore we have rotating magnetic fields are produced, okay? And you have another coil, so you have another, so you have rotating magnetic field. One is doing this, one is doing this, this. So once the rotor is rotating in synchronous with either of these two oppositely rotating air gaps, there is a force created by the magnetic system in an attempt to align them, okay? So that the minimum reluctance is maintained. So we're going to go from example here. So do I have an example? So in other words, I'll go back. Okay, go back, go back. So in other words, there's always a tendency you can get tracked to here or to here. So therefore causing this rotation, okay, causes rotation. Okay. For induction machines, okay, we have figure. So let's go through the rotor of both devices, identical in configurations. So either inductor or synchronous machines. So they are similar, okay? They are similar. Again, you have the windings sinusoid distributed. So you have rotating magnetic field. So you have an equivalent of the windings like orthogonally aligned, okay? So the operation, let's go to a picture here. Go to a picture here. It's quite the same as a synchronous machine, okay? Synchronous machine. I think we should have synchronous machine. So, so you have a single and two pole, two phase synchronous machine. This is, so you can see they look all similar, okay, all similar. It's a little bit hard to explain. Let me see. They look similar, but one of the several devices fall into what they call synchronous machine category. That means they go with the same speed. Okay. Single phase has very limited applications. The two phase, yeah, it's not much. Okay, but usually it's on the three phase synchronous machines. Okay. So in automobiles, aircrafts, utility system like pumps, okay, pumps and ships, they use the three phase. So we don't use a lot of two phase, single phase. We use three phases. So, but for illustration here, we use 1 and 2. Okay, 1, 2. Okay. So we have a field winding to generate a magnetic field that's rotating. The rotor is equipped with a short circuit winding in addition to this field winding to damp out the oscillation about synchronous speed. These windings are used to start or to unload the machine from store as an inductor motor. So what's the principle of operation? The current flow in the field winding is DC, okay? Although it may change in values by varying the applied field voltage, constant for steady state operation of a balanced two-phase synchronous machine. The stator winding connected to a balanced system, the state current produces a constant amplitude rotating magnetic field. So the magnetic amplitude is constant, but the air gap magnetic field is actually changing. Different position, I have different magnetic motive force. So the torque, to generate the torque or transmit any power, the air gap MMF produced by the stator, produced by the rotor, must rotate in unison, meaning synchronous, about the air gap of the machine. So that's why it's called synchronous machines. That's a motor and it's winding. One is single phase, one is two phase. But if that is hard for you to understand, let's probably focus more on permanent magnet device. Okay, permanent magnet device. So if we replace the rotor of the synchronous machine, the rotor itself is a permanent magnetic rotor. Okay, so that's actually help us to understand what's going on. Rotation of these devices is identical to that of a synchronous machine because the reluctance will be minimized if you turn. If we don't turn, there's a force to drag you. So let's see it. Okay. So now you see, because this is a permanent magnet, you have S and N, right? You have S and N. Okay. Because you have a sinusoid, generated. So therefore, here is the large. So it will move. N will go through here, and S will go through here. Okay. It will be attracted if this got an N, S. So N and S. So then N will go to S, S will go to N. So, or you have this is N, this is S. So anyway, S will go to N, N will go to S. Okay. So that they have an alignment. Okay, alignment. When you have alignment, your magnetic reluctance is minimal. So this is something we want to focus. BLDC. Okay, BLDC. So what's left now is rotating magnetic field through the AC excitation current by using three-phase magnetic field, or you use arrangement of the density of the coils to have a sinusoidal distributed coils. So permanent magnet DC motors will have brushes to transmit power to the armature winding. Okay, so this brush is really bad. It's called arcing effect. Okay, so this brushed, even if you use a permanent magnet, you have brushed version. versus brushless motion. So today we are going to mainly focus on a brushed BLDC, okay? So that we can throw away that brush and how it can be thrown away. So then we use something called electronic commutation, okay, to replace this brush commutation, okay. And this electronic commutation did such nice logic control such that it looks like very like a conventional DC motors. So therefore, DC motor system exhibits the same linear torque speed curve like we have seen in here, like this curve. So this is the speed, this is the torque, okay? This is the torque. Okay. And from external point of view, the BLDC and brushed DC, they have the same external characteristics. Okay, characteristics. So of course the benefits is clear, highly reliable. You don't have the brush. It's much quieter because the brush has a mechanical contact, so it will cause some noise. Okay, and it could be high speed because you have brush. You cannot go very high RPM, so maximum maybe just 10,000. It will have some. The brush will bounce. Okay, bounce. Will dance. Okay, will dance. For brushless, you can do a 10,000 RPM, 100,000 RPM, one order of magnitude. The downside is that electronic commutator, the cost is higher. Okay, the choice is not that wide as brushed DC. So the reason the cost is high because of the brushless DC motors have a complex machinery. Okay. So if something wrong, the fix is hard. Again, one of another thing to tell you is a high peak torque. Okay, because you can have windings on the stator housing. Okay, this gives efficient cooling. Okay, cooling allows high current to during the low duty cycle and lots of stop-start operation. Okay, like in an elevator. Okay, so the peak torque is can be 20 times. Okay, 20 times of their steady ratings. Okay, while in the conventional brushed DC motors, you probably can do only 10 times. So let me see. Another thing is called power density. Power density. So the power density is 5 times bigger, meaning per unit volume. So it's relatively smaller. Okay. So per unit volume of the power is called power density. Okay. So there are two types. One is called windings on a stator. Well, inside the rotor has less inertia, so it's for the start-stop operation. There's another type. It's called windings on a stator with a rotor on the outside. So rotor is outside. Outside rotor are better for constant load, high-speed applications. So I want to tell you that this has a name. It's called outrunner. So many of the small drone systems, they use the motor is outrunner. Okay, it's outrunner. So in other words, stator is the inside, rotor is outside. Okay, so the two types. One is the regular. Stator is outside, rotor is inside. Another one is a stator inside, rotor outside. So you need a constant load, high speed. Yeah, it's for the drone applications. Most of those are BLDC outrunner. Okay, outrunner. So we have said a lot of things here already, and let's try to understand what's going on. So basically, you say your angular velocity is rotation of omega r, okay, omega r, and theta is the angular displacement of the rotor measured from AS axis to the Q axis. So you need to understand the Q axis. So let's go from the beginning. So the magnetic axis, okay, for the stator winding will have AS, BS, S stands for stator, okay. Angular displacement about the stator is 5S, so 5S, okay, with references to the AX, okay. The angular displacement about the rotor is phi r, okay, the phi r reference at the Q axis, while the angular velocity is omega r theta r, angular as angular displacement of the rotor measured from ASX to the Q axis. So we'll see a picture here. Yeah, we'll see a picture here. So inside is permanent magnet, okay, permanent magnet. So it is a rotor inside, okay, the rotor is inside, stator is outside, but the stator, okay, stator is outside, okay, stator is outside. Now stator, you have windings arranged in such a way that stator is outside. So you have a arrangement such that the magnetic field is sinusoidally changing. So if we use AS and BS as my sensor here, so this is my position here. So I call this is AB axis, okay, AB axis. So AS, BS, so this is AS, BS, so this is a quadrature. So AS and BS, so they are perpendicular. So you have one coil in here and one coil in here. So you have two coils with 90 degrees apart, okay, 90 degrees apart. So each of these will produce a magnetic field, okay, that is changing along the circular position, okay. The circular position, let's use BS here as a starting point. So that is called phi S, okay. The QS is a body coordinates in the rotor. So this is my Q. This Q moves as the rotor moves, okay, rotor moves. So that moving is phi R, okay, phi R. And of course, on this shaft, you connect with torque. So you have omega R is you have load, torque load. So then the overall changing of the angle theta R, okay, theta R and phi R together will add in towards 5S, okay, 5S. So this angle goes this way, this phi angle goes here, so you will have these two add together, okay. So those derivations probably you can jump over because of this gap. So it looks similar until to the point. So this is something we are familiar. So this is acceleration, this is damping, this is load. We have providing torque. Again, okay, let me go back to this slide. I want to tell you. So this Q-axis is called a rotor reference frame. Okay. So Q is fixed on the rotor. So this is fixed on the rotor. Okay. Oh, let's see quickly where we can get into the familiar form. We still have some time. Oh yeah, we're all here. Okay, we are here. Okay, but you need to do some coordinate transformation to connect everything. So in the end, we lumped everything into Q and D. Okay, D is my stator. Okay, this is stator. Q is my rotor axis. Okay, but this type of connection, we can eventually talk about the voltage in here. Okay, voltage in here, and how they contribute back to this torque. This is the torque we provide from a motor. This is my load. I'm going to mechanical. So this is omega R. This is the rotation speed. Okay, multiplied by that. So you have different circuits. Writing a state variable, you should look like this. So this is how electronically doing what they called electronic commutator. Okay, so when you move to this A, B, C, these positions, we know the position, we detect the position. So I find you are coming here, then I suddenly change your providing the current in here. If I put in, if I rotate it to here, I need to change the commutation again. So then the excitation may go from here, okay, or here, okay, okay. So these are the possibilities. So basically, you have a switching logic to sequentially move, okay, while you detect the position of the rotor, okay. So you can see detecting that is not trivial. Okay? So electronic-wise, it's pretty complicated. Okay, pretty complicated. So I think I did very brief introduction of brushless DC motors. So in the end, this state equation is the same as brushed DC motors. How we can do the brush, we didn't do mechanically, we do electronically. So these are the brush commutation logic. So for the motor, it's so simple. So you have three terminals. You just provide the excitation to it, okay, to it. But how you provide it, it depends on the logic. Good news is today, you don't have to design. When I was a student, this is not showing up yet. So this is nothing mature, but today this is everybody can use. So there's something called ESC, okay, ESC. There's a dedicated chip, so you produce, depending on your throttle, okay, depending on your, what I'm doing. It's called throttle, okay? Depending on how many percentage of the application there, you add the throttle will be able to produce the logic corrected for this, as well as the amplitude, the strength, okay? So that the speed, omega, is under precise control. So this one is called, ESC is called electronic speed control. Electronic speed control. You hook up these terminals binding here. So this is ESC, okay? There are a lot of electronics here inside. I don't think you need to understand all the ESC internal, but you want to understand the working principle is rotating magnetic field. For BLDC, it's the same as brushed DC motors in external characteristics, okay? External characteristics. So with that, I think we broadly covered two types of DC motors. One is brushed, one is brushless, okay? Today's lecture is conceptual. In a sense that you understand something here. So you have a magnet here, N, you have a S, and N, and S. So you say you have some magnetic field in here. So you have a moving part in here. So you're moving this one here. So when you move, you will have a cutting magnetic field. But what if this is electronic? You can change N to S, or you can switch S to N, okay? So if this is a magnet like N and S, so if you are here, so I suddenly change this one to N, okay? Then this N will bring this one forward. So then when you move to here, then you have a SN. So you can change this one to N again. So you can change all these things. Okay, it's a magnetic field. You can change it by changing this one. Then it will make this move this direction. So this is actually a permanent magnet linear motors. Okay. So this is a permanent magnet. So these are the coils you can always change, okay? So then just by switching not commutation though, it's just like a rotating magnetic field. So you electronically switch it, you are going to make this motor to move forward linearly. That's a basic principle for linear motors. So to understand linear motors, you also need to understand this rotating magnetic, not a rotating magnetic, it's changing, okay, magnetic field. And then the basic principle is the reluctance will always go minimum way, minimum path, okay, minimum way. So as if you're switching all these things, then you are dragging this one moving forward, okay? That's the working principle. Our time is almost up. I know you have a lot of questions regarding your final exam and or maybe lab. So I suggest you meet me at Tuesday, 12 o'clock next week, okay? So today is Friday. I hope you have a good weekend. And anything you want to ask before we leave?
Professor?
Yes.
Can you hear me?
Yes, I can. David?
Yes. So I actually have a question about the project in terms of its grading. I was looking over the syllabus and see how the grades is broken down. Under what category will our final project be under?
That's 30% of the lab. In the lab, you also have different percentage for how much you grade. So that's a lab is 30%. So that final project is part of that 30%.
Okay, I just wanted to make sure. Let's see that
No,
correctly.
no, it's in our course you have a homework, quiz, midterm, final, plus
Yeah.
lab. Okay.
And will we be getting an update on our grades on our quizzes yet?
That's a very good question. I stopped doing quiz. I know everybody is struggling with the quiz taking and submission. So I stopped taking it. So I'm going to give, although it's a little bit not fair, but I'm going to skip that part.
Okay, no problem. All right, thank you very much.
Yeah. Okay. Any other questions? And I'll see you next Tuesday, 12 o'clock. Should I remind you guys? And if not, I'm going to stop today's lecture. Have a great weekend. Take care. Don't go anywhere. Stay at home. Okay. All right. Bye bye. See you. See you Tuesday noon.